All right. So this is a worksheet 11. We are going to explore the special theory of relativity. Let me make sure I'm recording. Everything's pinned. All right, we're looking good. So this one is the trickiness comes from the wording of the questions, right? So as long as you can isolate, your stationary from your moving frame, it's kind of straightforward. It's just application of equations. And then obviously we're going to expand on this with the relativistic momentum and all that other stuff next week. So for the time being, we're focusing on time dilation, the Lorentz transformation, and length contraction, okay? So we're going to go through each one of these equations in detail. However, I just want to bring attention to an equation 3 with length contraction. If you view the Google Docs, I made a comment of this, but just to be absolutely thorough, it should be where L naught equals the observer outside the frame of reference, and L equals the length measured from the observer within the frame of reference. So basically how it's natively written right now needs to be switched, right? So right now I have L and L naught. What's given on the worksheet, the definitions of them needs to be switched, but their locations in the equation are correct. So what I want to define here. So we have a stationary frame and we have a moving frame, right? And the stationary frame will experience the actual normal distance traveled. However, will experience the event over a longer amount of time, right? So it's a time dilation. And alternatively, with the moving frame, we will see a length contraction with respect to the distance traveled, and the event will be experienced in normal time, okay? So in either one of these cases, you can imagine the equation V equals D over T, right? And relative to the frame, that being stationary or moving, one of those variables, D or T, is relative. Obviously, with the stationary frame, the one who's experiencing time dilation, it is the time that is the relative variable. And with the moving frame, it is the distance that is relative, okay? And a little trick that I keep in my back pocket is just quantitatively, you can look at the variables provided and you can discern what is in reference to the stationary or moving frame. So what do I mean? We have our equations, delta t equals delta t naught divided by the square root of 1, etc. And then we have our length equation also, L equals L naught, square root 1 minus V over C squared, all that business, right? So starting with the time equation, delta t will always be larger than delta t naught. So what I mean by that is, and as I said before, what is in the stationary frame, that delta t will be bigger than, because time is dilated, than what's in the moving frame, which experiences the normal or proper time. I sometimes say normal, sometimes I say proper time. It's just the proper time, okay? And almost inversely, with the length equation, the stationary frame records the normal distance, and the moving frame, that being L, is going to have the contracted distance. Therefore, L is smaller than L naught. So just to set up to make the inequality clear here, delta t is always greater than delta t naught, and L is always less than L naught, okay? And that's again because delta t is the time dilated, it's slower, so it's larger. And L is contracted, so therefore it's smaller, okay? So sometimes I'll use that as a check. Like let's say I'm solving for delta t given delta t naught. And if my delta t comes out smaller than my delta t naught, I'm like, whoa, slow down. I messed up. And similarly, when I solve for using the length equation, if I solve for L given L naught and my L comes out smaller, I'm like, ruh-roh, I messed up. So that's a check. And the other thing you can do is if you're given both delta t and delta t naught, you can just quickly find which one's which, right? So let's say I'm given delta t as 5 and delta t naught, or excuse me, let's say I'm given 2 times in the question, 5 seconds and 1 second. I immediately know that the delta t, that being the one with respect to the stationary frame, is 5, and delta t naught is 1, and that's just because 5 is bigger than 1. So it's kind of a quick way you can decide what goes where, and that truth extends to the that extends to the length contraction. Also, apologies if there's a bunch of music. There's like a fair happening in front of Levy Library. I saw like a Ferris wheel, and there's music, and I don't know what else. Okay, so that kind of summarizes the worksheet talk here. And let's go over number one. So here we have a pion, which is an elementary particle that has a lifetime of 2.6 times 10 to the minus 8 when it's at rest. And we want to know how fast does it need to move such that the new lifetime is 5.5 times 10 to the minus 8 seconds. Okay, so this is the example I was talking about, where you can use what I described as like what's bigger and what's smaller to define delta t and delta t naught, right? So just by looking at this, we recall that delta t is always going to be larger than delta t naught, right? So delta t naught is 2.6 times 10 to the minus 8, and then delta t is the 5.5 times 10 to the minus 8. So we set up our question, question number one. We know the equation we're going to use. And I use delta t naught, but that's the same thing. Like this just here is delta t prime, but I just use the naught notation. Over is the square root of 1 minus v over c squared. Okay, so what do we know? We know delta t, we know delta t naught. What else? And what do we need to solve for? We need to solve for v, right? And we'll solve for v in terms of c. So you can like leave c on that side. So what do I mean by that? Let me show you. I'm going to get both of these values on the same side, and then I'm going to flip this so I don't have a 1 over this expression down here. So that's going to be delta t naught divided by delta t equals the square root of 1 minus v over c squared. And then you got to work this expression more, and eventually you'll come out to have v is equal to c over the square root of 1 minus delta t naught divided by delta t squared. V equals 0.88 c. So you can just leave it as that c. And when you have c here, you don't need to write meters per second just because it's implied with the c there. Okay, so a lot of these questions are kind of more of this flavor, and it just really like the thing that you need to keep in mind here is just like what's delta t and what's delta t naught. What's your stationary frame? What's your moving frame? Okay, so that's number one. We can move on to question number two now. I'll just do that over here. Gosh, the music is really loud. I hope that this recording doesn't get messed up. I wonder if I could, I guess I'll have to see at the end. Okay, so here we have a scientist that developed a special breed of cat that lives exactly 9 years. When Felix is born and is placed in a spaceship that blasts off with a speed of 0.8 c. We want to know how far from Earth, as measured by an observer on Earth, is Felix when it dies, and then how long it takes for the ship to send the message that the cat died back to Earth. So nice and horrifying question there. Okay, so we're given two things. We're given a time. Is it delta t or delta t naught? Well, it's delta t naught because it's the proper time, right? It's the actual length of time that the cat lives as measured on Earth. And we know the speed of the rocket or spaceship, whatever. So in part A here, we're asked to find how far the ship is going to be before the cat dies. So again, we know delta t naught. So we need to solve for delta t so we can plug that expression into v equals d over t and then rearrange that v equals d over t to get d equals v times t to assess a distance, right? But we don't know delta t yet. We only know delta t naught. So the first thing we do is solve for that delta t. And that's just the application of the equation that we've used previously. Okay, so plug in 9 years, plug in 0.8, the C's cancel out. What you get here is equal to 15 years. But you need to convert this 15 years to seconds. So I'm going to do this once, but I'm not going to keep doing it every single time because it kind of takes a while. We know how many days are in a year. We know how many hours are in a day. Apologies, I'm going to jump to the next board over here. So 24 hours in a day. Okay, does that look fine? Yeah, you can't even tell. Okay, and we know how many minutes are in an hour. So 1 hour, 60 minutes. And we know how many seconds are in a minute. So what cancels out? Minutes cancels out, hours cancel out, days cancel out, years cancels out. What we're left with is units and seconds, and that units and seconds is equal to, I see what I did. Okay, so that's how you solve for delta t, right? Apologies, I didn't actually plug in the values because I just combined this with the next step. So I'll explain, but I'll solve it the way I did. Okay, so we know what delta t equals. We know what it is in years, and you know what you after you do all this canceling out and multiplication, you know what it will be in seconds. So to actually find the distance, like I said, you need to use that v equals d over t equation, right? Where you're looking for d, so therefore you rearrange so you have d equals v delta t, right? Now you can plug in that delta t there, and the v is given, and what you'll get is d equals 1.14 times 10 to the minus 17. Sorry, bad handwriting there. Minus 17 meters, okay? Oh, I'm sorry, minus 17. That doesn't seem right. Apologies for that. 10 to the 17th meters. Okay? And all you're going to do here is take whatever you get in seconds and then multiply it by v, right? And they gave you v, which was 0.8 c. Okay? So the second, where 0.8 c equals that 3 times 10 to the 8 meters per second. So the seconds will cancel out, and all you're left with is units in terms of meters, and that's how you get that. Okay, so just basically take this guy from here to here, multiply it by what v is equal to, and then that's how you solve for t. Sorry, I didn't plug that into my calculator. Okay, and then in part B, we want to know when now the ship's going to send a signal back to Earth. We want to know how long that takes. Okay. So again, we're going to use that v equals d over t equation, except this time we're going to recognize the fact that, it's moving at relativistic speeds, c, and we want to know how long it takes back to send, so let's call it ts for the time to send, okay? And you can solve for ts just by rearranging the question here. So let's again rearrange. So ts is going to be equal to d over c, where d, we just solved for that. C is something that, it's 3 times 10 to the 8 there, which you should memorize. And using that, you can convert ts into seconds. So what comes out of plugging in d and c, which are two things we know, we get wait a minute, I didn't write this. Gosh. Here, let's write what I wrote. 1.14 times 10 to the 17 divided by 3 times 10 to the 8. And then you're going to take that TS, work it all out, and get rid of the units. TS comes out to be equal to 12 years. But that 12 years is not enough, right? Because we want to know how long after the ship left Earth. And we know that the ship left Earth 15 years ago, right? Or I'm sorry, that's how long the cat was alive on the ship before it died, right? Relative to the ship. So we'll say that 15 plus 12 equals 27 years. All right. So, yeah, sorry, I realized I didn't really like write all these steps out and solve them for you, but it's just unit conversion from Gen Chem. Kind of the important thing to note here is that, you know, on Earth, the proper time was 9 years. With the ship moving, the time is dilated, so it's 15 years. That's how long the cat lived. After the cat died, which was 15 years, it took 12 years to send the signal back. That's what we solve here. So therefore, from the moment the cat left Earth to the moment that they received the signal was 27 years. Okay, so let's make some room here. And work through question number 3. So here we have particle X. This is an elementary particle that has a lifetime of 2.6 times 10 to the 8 when it's at rest. How fast does X move if we observe X has a lifetime of 5.5 times 10 to the 8? This should be a similar sounding question. Okay. So question number 3. Again, we have these two things. This is to demonstrate like the quantitative difference between delta T and delta T naught. We have 2.6 times 10 to the 8, and we have 5.5 times 10 to the 8, right? And the key difference to remember is that the delta T will always be larger. So in this case, the delta T is 5.5 times 10 to the 8, and the delta T naught is 2.6 times 10 to the 8. So when we work this guy out using our time equation, we know what to plug in where. We know how to solve this. You know, we just, in the exact same way that we did number 1. And what we'll end up getting, you know, we get this expression, solve the exact same way. I'm going to skip a step because we're solving for V. So I'm just going to jump to that step where V equals C square root of 1 minus delta T naught divided by delta T. Okay. And V comes out to be 0.88 C. Awesome. All right. So that one's kind of not so crazy. And then we can consider question number 2 here. So let me erase over here. So for question number, I'm sorry, let's say 2, I'm at 4. For question number 4, we have Bob moves with respect to Alice with speed v. Bob and Alice are inertial observers, so they're both moving with each other, and their x-axes are aligned, so they're moving together like relative to each other on a straight line. Bob's velocity is along the x-axis. When Bob measures a time interval of 30 seconds on his watch, Alice measures a time interval of 45 seconds. So again, we have to remember, right? Delta T naught is smaller than delta T. So therefore, we know the stationary frame relative to the moving frame, where delta T is the stationary frame, right? And in part A, we want to determine speed V. Okay, so part A, this is exactly what we've been doing in many of these problems. Like this, and you know, I don't. We know how to do this type of question now. You solve for V. V comes out to be 0.745 C. All right. So now, kind of the hard part and the Lorentz transformation part of this question is Alice sees 2 flashes and they occur at x1 and t1. And the second one occurs at x2 and t2. According to Bob, what is the spatial separation between these 2 flashes? Okay, so we have to solve with the Lorentz transformation, where it's basically a relationship between 2 different coordinate frames that move together with a constant velocity, right? And they're relative to each other. So we defined the stationary frame previously. You know, that's Alice, because she's the one with that delta T. So what we need to do is solve for that x1 prime and x2 prime such that we can modify our equations to solve for what was it? What I want to solve for here? Oh yeah, for the x2 and x1, right? Which effectively we can solve for, you know, delta t and delta t1 and delta. The next step, yeah, it's delta t2 prime and delta 1 prime. Okay, so let's start with part B here. So the first thing we need to do is solve for x1 and x2. So we have those equations on the first page. I'll just write what we're plugging into, and then I'll give you their relative value. So x prime, 1 or 2, so we're either case, is going to equal to x minus vt divided by square root of 1 minus v squared over c squared. Okay, here's a little trick here. We're going to use this expression right here. We're going to put in parentheses many, many times. So rather than having to plug it into your calculator every single time, solve it from now, keep whatever it is, and only modify the top of the equation. So because nothing down here is changing, right? Everything, all these variables down here have been defined. So what that's equal to is, or how I like to plug everything in is x equals v over t. I'm sorry, x minus v times t divided by 0.667. Okay, now I don't need to plug in all that nonsense every single time. So in both cases, v is something we know. It's 2.23 times 10 to the 8. You know, that's what you get when you solve in part A. And we know the time, 10 to the minus 8. And the only difference between x1 and x2 is what we plug in for this x value, right? So when you plug in appropriately, where x for x1 prime equals 40, and then x for x2 prime equals 60, you'll find that x1 prime is going to be equal to 56.6 meters. And then x2 prime is going to be equal to 74.9 meters. Okay. Now you can find the difference between them. You know, delta x prime equals x2 prime minus x1 prime. And that difference is equal to 18.3 meters. So, all right, delta x prime is equal to 18.3 meters. Okay, so this is the spatial separation as seen by Bob. What we've done here is we've taken the distances experienced by Alice and modified them such that, like, within these two frames that are moving, we can see what they are relative to Bob. Okay, so that brings us to part C, where we're now going to look at time. So in part C, we're seeing that Bob, according to Bob, what is the temporal separation between these two flashes? So much as with part B, we're given the times experienced by Alice, and now we need to modify them such that we know what they are for Bob. So let's see here. Part 3, or part C. The equation we're going to be using is t prime is equal to t, that's what's changing, minus v over c squared times x divided by the square root of 1 minus v squared over c squared. So now you have the equation. I'm going to bring notice to a few things here. First is we need to know x. So we're going to use what was previously used to solve for that t prime there. And also this denominator is the same as what it was in part A and part B. So like I said, you're going to be plugging it in a lot to your calculator. If you know what it is from the beginning, it'll save you a little bit of time. So how do we solve this part here? Very similarly, we're just going to plug in the relative times and everything. So for, let's say, T1, we're going to plug in 10 to the minus 8 and then 40. And then for T2, we're going to plug in 4.5 times 10 to the minus 8 and 60. Okay. And then you just solve for them and you end up getting delta t, which is going to be equal to, that t2 prime minus t1 prime is going to be equal to minus 1.5 times 10 to the minus 7 seconds plus 1.34 times 10 minus 7 seconds. So Bob is experiencing something that's flipped, right? Both of those things are negative. So that equals negative 0.21 times 10 to the minus 7. Let me make that minus 7 a little bit more clear. Okay. So again, it's just augmenting those equations that we've now used a few times. And then lastly, let's enter question 5. So like I said during my in-person session, question 5 is very difficult. So I want to dedicate at least 30 minutes to solve it here. So again, we have a particle traveling through the Earth's atmosphere at a speed of 0.75 c to an Earth-bound observer. The distance it travels is 2.5 kilometers. How far does the particle travel in the particle's frame of reference? Okay, so we know the stationary frame, which is L. So this is number 5. L naught equals 2.5. Okay, of kilometers, and this is a stationary frame. So now we're looking for L, and expectedly L is going to be smaller. So that's kind of like I said. Remember, L is going to always be smaller than L naught. So tip you off to think like that. So we're expecting a length contraction. That's what we're solving for. So what equation do we use? All right, so stick with me here. L equals L naught, which is 2.5, square root of 1 minus V over C. So they give us that. So it's 0.75 C divided by C, all this squared. The C's cancel out, and L equals 1.65 kilometers. And gotcha. That's all it is. It's an easy one, but I tricked you. Thought you're going to have a lot of work to do, but it's not that hard. It's just a simple definition question. So first, get pranked. Second, the important thing here is just like it's powerful to recognize the quantitative difference between delta T naught and T and L naught and L, right? Just for thorough purposes, delta T will always be larger than delta T naught, and that is because the stationary frame will see the time dilated event, and the L will always be smaller than the L naught, and that is because the moving frame will see the distance contracted, right? It'll be shorter. Okay, and that wraps up this worksheet. And good luck. Let me know if you have any questions. Homework review tomorrow. All right, thanks, guys.